Okay, so what I want to do now is on these examples to look at, well, what if you have a vector valued function that you're trying to integrate? And just like derivatives, these vectors have two components: a component that represents an x and a component that represents a y. And really, it just means you have to do both. So it's like a 2-for-1. You get double. And so I look at this first example and I see, wow, the x component is quadratic in the denominator, and in my head, I'm thinking about different techniques. It could be an inverse trig function. I might have to factor partial fractions, things like that. And then I have cosine squared, which, is something that we have to rewrite using a half angle formula. So great, we have two wonderful review integrals to do here. So but I guess my point, I guess I got so excited about doing the integrals. My point is that you just integrate each of the components, and just don't forget, in this case, like here, we would have to make sure that we put a plus c in each of the values. So I noticed that t squared minus t minus 20 can factor. So I'm thinking, let's do like partial fractions. Good review, right? So 9 over t, what is that, minus 5 times t plus 4. And so remember, we'll break that down. So let's say it's like a over t minus 5 plus b over t plus 4. Now I'm also thinking in my head that we could rewrite this as using a power series, endless possibilities here, but I'm not actually looking for the sum of this. So I know it's not necessary, but of course, anytime I can use Taylor series, power series, right? How exciting. So we'll clear out our fraction. So 9 equals a times t plus 4 plus b times t minus 5. And again, like if you remember how this works, we pick out t. So let's let t equal 5. So that means our equation is 9 equals 9a. I think I picked a pretty nice example, plus 0. So that means a is 1. And then if I let t equal another value, let's say, negative 4, we still have 9 equals, that goes away, negative 9b, therefore b equals negative 1. So I thought I came up with a pretty relatively simple partial fractions here to solve. So we'll just do the first part. So we're going to integrate, let's see, our a value, so 1 over t minus 5 minus 1 over t plus 4 dt. And so, just as a good review, that since the coefficients of t are just a 1, when I do this antiderivative for natural log, there's no extra chain rule, there's no U-Substitution. I don't have to worry about that, which is nice. Okay, so back to pen. So then I could do the natural log absolute value of t minus 5 minus natural log of t plus 4 plus c. So here represents my x component of the vector valued antiderivative. Now, whether or not you combine the natural log, completely up to you. You could make that natural log of t minus 5 divided by t plus 4 plus c. That's fine too. Okay, now to integrate cosine squared, remember we need to utilize a half angle formula. And so for that half angle formula, so cosine of theta over 2 is equal to 1/2 plus 1/2 cosine of theta. Or whatever we see out here is always going to be half of what we would be integrating. So in our case, I know that cosine of 6t, this is cosine squared, my bad. So then let me just redo that. There we go. There we go. So then it's like cosine squared of 6t is equivalent to 1/2 plus 1/2 normal cosine of 12t. And again, thinking about the half angle formula, this angle, that was lovely. This angle here is always half of what we're going to put inside. Now, the only difference if it was sine squared, remember sine squared, just as a good review, sine squared, the only thing that changes, if it were sine squared of just an arbitrary theta, the only difference, it's 1/2 minus 1/2. It's still the cosine function of 2 theta. Again, looking at that relationship between the two. The angle becomes doubled out here, and that allows us to rewrite it just as a cosine function. But for us, it's cosine squared of 6t, so it's this one right here. So let's go ahead and integrate that. So we do the integral of 1/2 plus 1/2 cosine of 12t dt. So that's just linear for the first part, 1/2 t plus 1/2. We pick up an extra 1/12 here. If I did a U-substitution, antiderivative of cosine, think, be careful. Sine, it's positive, 12t plus our constant of integration. And so again, that becomes like a 1/24th in that first coefficient. So I could say it's 1/2 t plus 1/24th sine of 12t plus c. Remember, our answer is a vector valued function, so we need to go ahead and I guess give it as a vector. So that bracket there, the natural log of t minus 5 over t plus 4 plus whatever the x component's constant of integration is, and then 1/2 t plus 1/24th sine of 12t plus its constant of integration. So there it is, vector valued function. Okay, now a lot of times they'll give us some initial conditions so we could solve for those c values, and I think that's what's going to happen in our next example. All right, so it says suppose the acceleration, I don't know why that dot's there. Well, there we go. Suppose acceleration of a particle moving along the xy plane is given by a of t is equal to this function here. It's given an initial velocity condition and an initial position condition. Find the values of the velocity at 3 and the position at 3. So we're going to have to do 2 iterations of integration because we need a velocity valued vector and also a position valued vector. And the fact that they gave us some initial conditions, first the initial condition of velocity is going to allow us to solve for that particular constant of integration, and then they also give us the position one. So let's first look at doing the antiderivative of the vector valued function that's been given as acceleration. Oh, look at that big bright orange highlight, but I wanted pen. There we go. So if I integrate that, so if I'm integrating a of t dt, that'll give me my vector that represents velocity plus some constant of integration. Okay, so it's kind of the format. So if I integrate 6t, I could do that one, that's 3t squared plus some constant. And then antiderivative of negative sine. Well, the antiderivative of sine is negative cosine, so it's negative, so it actually becomes cosine. But the fact there's a 2 there actually is a 1/2 cosine of 2t plus c. And if you're wondering, oh, Mr. Brown, I need just a quick reminder of, where did this 1/2 come from? Well, it has to do with the fact that your original function had a 2t. So if I think about that as just a mini u substitution, if you're letting u equal 2t, du is 2 dt, so we have 1/2 of the du is equal to dt. So now when I integrate 1/2 times negative sine of u du, I know the antiderivative of negative sine will be a positive cosine, and there's the 1/2. So it's 1/2 cosine of u plus c, or 1/2 cosine of 2t plus c. And again, I think you guys remember the pattern that whatever this is, it's going to be a reciprocal here to anticipate that chain rule when I do the derivative. Now, initial value, when the velocity, when t is 0, here's our initial condition of velocity. So when v is, the x component is 0, our initial condition is 2. So 2 is equal to 3 times 0 squared plus c, which means 2 is that condition's initial starting point. 1 is equal to 1/2 cosine of 0 plus c. Well, remember, cosine of 0 is 1, and 1 times half is half. So 1 equals 1/2 plus c. I said c. So therefore, c is equal to 1/2. So now my vector that represents velocity now has definite points. So my vector that represents velocity is equal to 3t squared plus 2, and then 1/2 cosine of 2t plus 1/2. Excellent. Now I'm going to come back to that when I start evaluating, when I need to start evaluating what is the velocity at 3. But let's go ahead and just integrate one more time to get the position. And so if I integrate that function, and again, just thinking schematically, if I integrate velocity with respect to time, I will get its position vector plus its initial condition as a constant. So let's integrate. So again, integrating 3t squared plus 2, that becomes t cubed, which is nice. And let's see, put a vector there. So t cubed plus 2t plus its constant. And then when I integrate this, again, this 2 is going to come out as the front to be another 1/2 because of that chain rule. And remember, antiderivative of cosine is positive sign. So I have 1/2 times 1/2 sine of 2t plus 1/2 t plus its constant. Okay, so then let's go figure out the initial conditions, -4, 0. So this thing is equal to -4 when time is 0. So that was nice. Our constant is -4. And then this thing was equal to 0. So that's 1/4 sine of 0 plus 0 plus c. Sine of 0 is 0, so we know in this case 0 is our constant. Okay, so then we'll write down our position function as a vector valued function, which would be s of t is equal to, bracket, 3t, oh, just kidding, I was looking at the antiderivative, or looking at the derivative, my bad. S of t is equal to the vector, here it is, t cubed plus 2t plus our constant of -4. So let's just make that -4. And then the y component we said was 1/4 sine of 2t plus 1/2 t. Okay, so there it is. And I just have to evaluate 3. So if I put in 3 to the velocity function, so v of 3, so that equals 3 squared is 9. 9 times 3 is 27, plus 2 is 29. And then if I put in 3 here, I get the cosine of 6, which I don't know. It's fine. Just leave it as cosine of 6 radians plus 1/2. Okay, in terms of the position, so s of 3. So then, 3 cubed is 27. 27 plus 6 is 33. Minus 4 becomes 29. Well, that's odd. It's exact same as this. Did I do the math right? 3 squared is 9. 9 times 3 is 27. 27 plus 2 is 29. So its initial velocity component is 29. How ironic that its initial position component, 27 minus 4 is 23 plus 6 is also 29. Oh, what a great day. 1/4 sine. Now, if I completely made a mistake and it's a very obvious one, send me an email. Let me know. Sine of 6 plus, and then 1/2 of 3, which is 3/2. So there would represent its position vector. And again, remember, these vectors, at least the position vector, remember, it's relative to the origin. So wherever it's starting, it'd be pointing in a certain direction. And then the velocity vector would just go off of that tail. So it'd be going in this direction to represent maybe the slope of the tangent line right there. Okay, so I think we've answered those questions there. We found those vectors. Excellent. So then there's one more example, I think, on our notes page. And I like this example from a standpoint that it shows an older notation that doesn't often come out necessarily, on the AP exam, but every once in a while it does. And this is the notation that we actually use in honors pre-calc, so it might look familiar. This I and J. And so here's here's a vector that represents r, whatever that is, at 0 when time equals 0. It's like 3 in the x direction and -1 in the y direction, and the I and the j just are indicating that these are vectors. So another way I could have written this is just bracket 3 comma -1, but just a different notation. We're just calling it 3i minus j. Same thing here. This could have been written as 1 over the square root of 1 minus t squared, comma, the square root of 4t plus 1. So it's just another way to write that vector valued function. And notice that it's given as a derivative. So this is the derivative. We want to know the normal function, and we also are given an initial condition. So just same as last one, we're going to integrate each of the components. And again, I like it. It's like a 2-for-1. So this first guy, if I'm going to integrate 1 over the square root of 1 minus t squared, I'm very excited to notice its inverse sign. It's quadratic, that's trapped in that square root, right? Our a is just 1, so 1 squared is 1. So this becomes just arc sine of t over 1 plus our constant. And if we notice that when t is 0, we get 3 as our value. So I could say 3 is equal to the arc sine of 0 plus c. Arc sine of 0 is 0, so I know our constant is 3. So now I know for our x component of this function, I know that it is arc sine of t plus 3. Okay, now this one right here, this one is going to be, if you want to use a U-substitution, you're integrating a square root. You could let u equal 4t plus 1. Its derivative is 4 dt. We have 1/4 of it. So we have 1/4 du equals dt. So when we integrate, we'll have 1/4 the square root of u du. Remember, this is the 1/2 power, so you bump it up a power and divide by that power, which is u to the 3/2 divided by 3/2. And if you've done these enough, that u to 3/2 is like u root u. The 3/2 slips to 2/3. So I have 2/3 times 1/4 of a u root u plus c. And then we go back and substitute that in, 2/12, which is 1/6. And our u is 4t plus 1 times the square root of 4t plus 1 plus constant. This has a vector initial condition of -1. So -1 is equal to 1/6, I should say, 1 times 1 plus c. So it looks like -1 is equal to 1/6 plus c. So it looks like c should be -7/6. All right. So then we go ahead and just put that together. So we have, and even if you want to leave that, I'm noticing we could just leave it as a 3/2 power if you want. So we have 1/6 times the quantity, 4t plus 1 to the 3/2 minus 7/6. And we put it all together because it does ask for us to find it as a vector. It's a vector valued function. So r is equal to, and I'll go with the newer notation, arc sine of t plus 3, comma, maybe put parentheses here, so I know the 3 is outside, 1/6 times 4t plus 1 to the 3/2 minus 7/6, like that. So Again, nothing really super, I think, different here. You're just integrating component by component. I think with the derivatives, we had a little bit more, only because we were just showing them what they're represented. Okay, so take a look at the second vector worksheet, and there's a lot of application and other kinds of examples that you're going to have to integrate. Check out the solutions online, and then if there's other questions, send them as an email, and